So we're in 2.3 and we're looking at properties of functions, and we're going to begin looking at maximums and minimums. So there are different types of maximums and minimums. We're going to begin looking at what's called a local max. So let's say you have a function. It has a local max at a particular x value called c, provided f of c is bigger than all the f of x values in some interval about c. Now here's the idea. So here's my x-axis. Here's some number c. And then we have some function, maybe doing like this. We have like a hilltop here at c. So if I take c and trace it back to the graph, and I trace that back to the y-axis over here, here's f of c. So f of c is going to be the largest y value in some little interval here. So if I focus on this little region, f of c is going to be the highest point in that little local region. Doesn't have to be the highest point on the entire graph, but just in this little local region here, this little interval about c. Now basically, a local max occurs at like a hilltop. So local max occurs at a hilltop or a mountaintop. So you may also see it something, I don't know, you may see something like this. And down here you'd have C. Or you'd have a local max here. There'd be a local max there. This one would have had a local max as well. They're like mountaintops, hilltops, you have local maxes. Okay, so that's a local max. Let's talk about a local min. A function f has a local minimum. At some x value, which we're going to call c, a particular x value called c, provided the following happens. F of c is smaller than all the other outputs for all x values in some interval about c. Let's draw a picture. So here's a c on the x-axis, and let's say our function looks something like this. Locally here. Who knows, it might do some other stuff, but around C, there's this little dip. There's this little valley here around C. So if I were to locate C here, and if I were to find where the graph is, it's right here, and I trace that back to the, let's say this is the y-axis over here. That output's going to be f of c. Notice that f of c right here is going to be the lowest y value in this, okay, let me take an interval here, this little region right here. So f of c doesn't necessarily have to be the lowest point on the graph, but just in some little interval, some local area around c, it's the lowest point. So local minimum, let's say local min is basically a valley. A valley that's on the graph. That's a local min there. It could look something like this as well, or this as well. No, get the right color. Now this would be a local min as well. Local min right here. And that little valley. Local min at x equals c. Okay, so we have local max and local min. So these are little high spots and little low spots. I'm going to talk about absolute maxes and absolute mins now. Absolute max and absolute min. Okay, I'm going to have to do some erasing, I guess. Fit this on here. Didn't give myself enough space. Don't like doing this, or I have to erase. It's no fun. Okay, here we go. So we're going to do a definition. What is a absolute max? So not a local max, absolute max. So a function f has an absolute maximum at some particular x value, let's call it u, provided the following happens. F of x is less than f of u for all x values, every single x value. So that means f of u is the absolute highest y value on the graph. So, yeah, let's draw a picture. Maybe I got something like this. Okay. And let's say right here we have u. So if I take u, hit the graph, and I trace this back to my y, let's say my y-axis over here, that outputs f of u. And f of u is going to be the absolute highest y value on this graph, right? There's no y value that's above f of u on the graph. So it's the highest place. So this here is the absolute max at u. Okay. So you have some other maxes here, right? You have a max here. That would be a local max. You have a local max here. And at u, you have a local max, but u is the absolute max as well. So you only have one absolute max in this instance here. Okay, another definition. Let's talk about absolute min. Absolute min. A function f has an absolute minimum at some particular x value. Let's call it v. Call it v. Provided the following happens. F of v is smaller than all the other outputs, f of x. This is for every single x value. So do an example of that. Let's say I had a graph that did something like this. Red, let me make it red. Come on, red. There you go. This is my function f. And right here, this is going to be my v. So if I take v and I hit the graph and I trace this back to the y-axis, f of v is going to be the smallest y value on this entire graph. So this right here is the absolute min. So you may have some other local mins, like you may have a local min here, and you may have a local min here, and a local min here, these valleys. The absolute min itself is going to be a local min, but there's only one absolute min in this case. Okay, so what we want to do some examples. So we're going to go to some graphs that we've already seen, but the instructions are going to be different than earlier. Here we're going to identify local maxes and local mins, absolute maxes and absolute mins. So to determine the x values, where the function has a or an 1, local maximum. So first, find any local maximums. 2, second thing you want to do is determine any local minimums, if there are any, and give the x value for which they occur. Number 3, you want to determine if there are any, absolute maximums. And if there are, give the x value. And number 4, determine if there are any absolute minimums. And if there are, give the x values for where they occur. Okay. Where does a function have a local max, local min, absolute max, absolute min? So we're going to start here. We're going to do local max. I'll write it this way, f does f have any local maxes? Yeah, right, there's going to be a high place here. Oh, come on, that sucks. There it goes. So local max is a high place here, a high place here. So these aren't the highest places necessarily, the absolutely highest place, but just high places like mountaintops or hilltops. So f has local maximums at x equals c and at x equals e. Okay, let's identify, are there any local minimums? So to be a local minimum, you have to be a valley. You have to have two sides. So that would not be a local minimum because it only has one side. That would not be a local minimum because it only has one side. So there's only one local minimum here. F has a local minimum at x equals d. So just one. Now, is there an absolute max, an absolutely highest place on this graph? Yeah, right here, right? That's where the absolute max is at E. It's the highest place. So F has an absolute max at x equals E. So notice at E you have an absolute max and a local max. And number 4, what about any absolute mins, any absolutely lowest places on the graph? F has, yes, there's one down here, right? That's the absolute, there's nothing below that place. It's the absolutely lowest place on the graph. Has an absolute min at, that would be x equals a. Okay, so we're going to do the same thing for our next graph. So we've seen this graph earlier when we were doing with increasing and decreasing, but now we're going to apply that to the maximums and the minimums. Erasing. Okay, so what color am I using? I forgot what colors. Okay, blue, green. So we're going to do a local max first. This graph, okay, this graph is called G. Let's use the letter G for that. G, are there any local maxes? Yeah, there's going to be one hilltop right here, or mountaintop there. This is not on the far left. That is not, number 1, because it's not even part of the graph there, right? You have an open circle, it's not part of the graph. Number 2, it doesn't have a left side to it, so Not including that. How about that? Is that a local max? No. There should actually be two sides to it, right? There should be two sides to it to be a local max. This only has one side. So we're not going to include that. So we're only going to have one local max here. One local max. Okay, so G has a local max at, where's that at? That blue one we circled is 8, right? X equals 8. Okay, let's see local min. So these would be valleys. You have to have two sides. So we have a valley here at 9. We have a valley here at 6. Do we have a valley here at 2? No, that is not actually part of the graph, right? At 2 you have an open circle, so no. It's not part of the graph, so we're going to get rid of that one. So we just have 2, 6, and 9. So number 2, G has a local minimum at x equals 6 and x equals 9. Okay, now we're looking for absolute max. Is there any absolute highest place to the graph? No, if you look at this graph, it continues going right forever to the right. So it keeps going up and up and up and up and up forever. So there is no absolutely highest place. So G has no absolute maximum. There is none. Is there an absolutely lowest place on the graph? Well, you might think right here is the lowest place on the graph, but that is not the lowest place because that's not part of the graph. Not part of the graph. So it turns out that the y values, they keep going down and they get closer and closer and closer to 1 as a y value, but they never get there. Like you get like, you can say you have 1.01, 1.0001, 1.000001, 1.000001. So those y values get closer and closer and closer and closer to 1, but never quite get there on the graph. So there is going to be no absolute minimum here. G has no absolute minimum. Yeah, think about that one more time. So I'm coming down, so imagine arrows pointing down here, and they're approaching that hole. So as you go down, the y values are going to get closer and closer and closer to 1, right? Closer to 1, but they never get there, right? They get arbitrary close to 1. 1.00000001. 1.00000001. They keep getting smaller and smaller, but they never quite get to 1, the y values there. Yeah, so there are infinitely many y values that get smaller and smaller and smaller and smaller, arbitrary close to 1, but never quite get there. So sometimes you don't have absolute maxes, sometimes you don't have absolute mins. You get all kind of weird combinations. All right. So I think that's going to cover it for our properties